So 7 properties of logarithms we're going to look at here. One of them, just in this yellow box here, we have some basic properties, and then over here we'll have the ones that we're going to focus on, the product law, quotient law, and power law. But log base a of b is only defined when a and b are greater than 0. We mentioned that when we started talking about logarithmic functions. They are only defined when both the base and the argument are greater than 0. Log base a of 1 is 0. The reason for that is if you use the definition, a to the 0 is equal to 1. A to the log base a of b equals b. And if you were to think of that kind of like there's a sort of a canceling out that's going on here. We've done this already. This is what we've used to solve equations that we needed to take the log of each side of. The fact that a to the log base a of b equals b. And then we also have here log base a of a to the b equals b. So those two are closely related. Those are the basic properties of logarithms. We've used those already in solving logarithmic equations. So the product law. Might even want to show you something. Let me so product law says that the log of the product, v times w, is equal to log of v plus log of w. That's just another way of saying that if logarithms are exponents and you're multiplying two exponential functions or two things that have the same base, right here we would have log base 10, then it's the same as adding them. So that's what we're doing right here. Is when we have two bases that are the same and we're multiplying, we add the powers. That's all that this is saying. So if logarithms are powers or exponents, when you multiply, we have log base whatever. In this case, it's base 10 of v times w. It's equal to log of v plus log of w. And then we can go in reverse here. If you have log of v plus log of w, it can be written as log of the product of the two. And in calculus, what we'll do is take logarithmic expressions and rewrite them in such a way that we can then differentiate or integrate them more easily. And so these rules show up quite a bit in calculus. So being able to separate them, we're actually going to usually simplifying is taking these two terms and making them into one. But in calculus, we'll take a single term that's a log of the product of several functions and break them up into a sum, and then take the derivative or the integral of each one individually. The quotient law is log of v over w. That might be a better way to write that rather than v divided by w. This is written when we didn't have maybe math type on here, but log of v over w, I would probably write it that way. Here's what I mean by that. Okay, equals log of v minus log of w. And so log of the quotient is equal to the difference of the logs, is what that's saying. And that you've seen before as well. You've seen it when we've done, say, a to the m divided by a to the n is a to the m minus n. We subtract the two powers, and so that's what we're saying here. We're subtracting the two logarithms, and the logarithms are powers. And then the power law says log of v to the k is the same as or is equal to the product of k times log of v. And this we have used in our equation solving over and over again. That has as its parallel the fact that if you have a to the m all to the n, it's equal to a to the mn. Power to power you multiply. All right, so we're going to use either the properties in this yellow box here or the three laws that I put up here to find the value or values of these logarithmic expressions. So log base 3 of 3 to the 71, you see which one that fits into? Which one does it fit here? Match. You see right here how it matches this guy? You see that? Here the base is 3, the argument is 3, and the power is 71. And what's this saying? If we have log base 3 of 3 to the 71, it's 71. Yeah. That property says. That's it. And which one does the next one fit here? What's that? Third one, yeah, it's fitting this one right here. So we have, instead of A, we have E. Instead of log base A, we have log base E, right? And so this is telling me that this must be 6. Then, the next one. Before I can find the value of that without a calculator, I need to apply one of the laws to this. And we're actually going in reverse here. We're going to take this, which matches up with the right-hand side of the product law, and write it in terms of the left-hand side of the product law. And so this would be the same as log base 8 of 16 times 4, or log base 8 of 64. Now, if I want to evaluate that, I need to think about, well, perhaps rewriting it as an exponential function using the definition. Or, in logarithmic form, see if I can rewrite the 64 so that its base matches the 8. And that's what we're going to do in this case. So we have log base 8 of 8 to the second. We're going to take 64 and think of that as 8 to the second. And now you should see that it matches. Yeah, it matches number 1, so it's just equal to 2. Log base 8 of 8 squared is 2. You know, another way to think about this would be, okay, if this, say, equaled x up here, I would be asking the question, 8 to what power equals 64? Right? So if you're more comfortable with exponential equations, you could rewrite this at this point as 8 to the x equals 64, and then change it to same bases. 64 would be the same as 8 squared, so x must equal 2, or use guess and check process here. All right, the next one. We're going to rewrite this one. This one matches with this one right here. So we're going to rewrite it going backwards. This would be the same as log base 6 of 108 divided by 3, or log base 6 of 36. So kind of similar to the one we just did. 36 could be rewritten as log base 6 of 6 squared, which equals 2 again. So rewriting that log of the difference of the logs as a single logarithm of the quotient of those two. All right, number 5 utilizes couple different properties, at least 2 I see here. We have 5, log base 5 of 6. Do you see which one in the yellow box that fits with? It looks like it's, yeah, the third one down here. And so 5 log base 5 of 6 is going to equal 6. Right? This whole piece will equal just 6. 5 log base 5 of 6. Plus log base 5 of 7. Well, here we have 6 plus, well, it's not just 7, but 6 plus log base 5 of 7. What else could we do with this? Oh, let's see. Sorry, I didn't write this right. It's not correct. Here's why. Sorry about that. The whole thing is part of the exponent, right? You see that? So I apologize. Let's break this up then. You're right. Some of you are right. You saw ahead. This is part of the exponent. So I think we better, before we change this to a 6, which is correct, we need to think of this, kind of undo it. So we have, if I were to work backwards, I have 5 log base 5 of 6 times 5 log base 5 of 7. Let me explain that here. This whole thing, which I wasn't seeing for some reason, is the exponent on the 5. That whole thing is the exponent on the 5. So it would be like working backwards from something like a to the m plus n power, right? That's what this is like. It's like the m is this log base 5 of 6, the n is log base 5 of 7. So if I work backwards from that according to my laws of exponents, it's a to the m times a to the n. And this is something we use frequently in calculus, is kind of breaking it back apart again. And so that's what I'm doing here, is I'm breaking this apart into a product of 2 values, both with the same base. And now I can go ahead and apply these 2 basic properties up here. One of them is exactly this here. That's equal to 6. And this other one, we have 5 log base 5 of 7 is also equal to that same one. So times 7. And 6 times 7 is 42. So you're right with the 42. Okay, any questions on that? So there's going to be just a set of problems in the book where you have to use, really there are 6 properties here, and then this deals with the domain of the argument and the value that the base can be. All right. Back before we had calculators, there was a whole list of a table, basically a table of values, where you would be given log base 10 or log base e or ln of all of the prime numbers, all the prime numbers. And so the fundamental theorem of arithmetic says that you can take any positive whole number and using the factor tree, right, write it as a product of primes to different powers. And between this power law and the fundamental theorem of arithmetic, you could rewrite then any of these numbers, even some decimals here, as a product or a quotient of prime numbers, and then also use the quotient and product laws to write them then as a sum and difference of logs. And so once you do that, then all you need to know is things like the value of ln of 2, ln of 3, ln of 5, ln of 7. You with me here? And like ln of 8 you wouldn't need to know, because ln of 8 would be made up of ln of 2 and ln of 2. If you thought of it as like ln of 8 would be the same as ln of 2 to the third. You can move the 3 out front and have 3 times whatever ln of 2 is. So all you needed to know was the value of all those, of the log ln or log base 10 of those prime numbers. And so that was traditionally what we did here. It's a good way to just practice using the properties. In other words, I can take ln of 6 and break it up into ln of 2 times 3. Let's behave here. So I can take ln of 6 and break it up as ln of 2 times 3. There we go. And ln of 2 times 3, according to the product law up above here, can be rewritten as ln of 2 plus ln of 3. And if I know the values of ln of 2, I just put in a and b. If you type in your calculator ln of 2, you get a decimal approximation to what that's equal to. ln of 3 is something different. But if I replace ln of 2 with a and ln of 3 with b, I get the expression a plus b. So if you know what ln of 2 is, you know what ln of 3 is, you could then find the value of that. This one's not as obvious. ln of 1.5, I think it will be easier to see once I rewrite this as ln of 3 over 2. Not real obvious, ln of 1.5. But how are we going to involve 3's and 2's in this? Well, if you think of it as ln of 3 over 2, then we have ln of 3 minus ln of 2 according to the quotient law. And ln of 3 was b, and ln of 2 was a, so I have b minus a for that one. So how could I rewrite ln of 27 as ln of 3's or ln of 2's? Yeah. Yep, 3 ln of 3. So this is the same as ln of 3 cubed, which by the power law is 3 ln of 3. And if I replace ln of 3 with b, I get the expression 3b. This one, that is a little fourth root of 2 over 3. We can see that we do have a quotient there. We might want to rewrite this using the power law first. So this is the same as ln of 2 over 3 to the power of 1/4. Okay, so that's ln of 2 over 3. They're funky parentheses. Sorry about that. The board is glitching out again. So ln of 2 over 3. And spooky look like wings, bat wings. It's for October. Halloween. Yeah. So have you seen this written in this way? Fourth root of 2/3 is the same as 2/3 to the 1/4 power. Cube root would be to the 1/3 power. So now, using the power law, I can move that out front. So we have 1/4, and I have ln of, let's put this in parentheses, the 1/4 is all the way out front, and we have ln of 2 minus ln of 3 in this case. It's really frustrating. So ln of 2 is A, and ln of 3 is B. Yes, so this would be 1/4, and then you could write it as A minus B. Okay, or you could also write it as 1/4 A minus 1/4 B if you distribute it. So you're going to be asked not only to find exact values, but also to take some logarithmic expressions, rewrite them using those laws. That's all you're going to do. Is those basically those 6 laws of logarithms to rewrite things or to evaluate things. And all of it can be done on your calculator. I understand that you could take any of these, type it into your calculator, get a decimal approximation. But we're just working on understanding these laws and basic rules about logarithms. So number 10, it says write each expression as a sum and or difference of logarithms. Express powers as factors. So in other words, we don't want any powers left on any of the variables in there, okay? So on this first one here, this is log base A of u squared v cubed. So the first thing we can do is rewrite this as log base A of u squared plus log base A of v cubed. That's applying the product law. So this time we're going from the left to the right. So a log of the product is equal to the sum of the logs. And now when I say express powers as factors, that means I don't want any powers on these letters in my final answer. So then I'm going to use law number 3, the power to a power rule, and move those powers down out in front. So I have 2 log of A plus 3 log of u. Base is A. Try that again. So log base A of u plus log 3 log base A of v. And this is actually what we do in calculus. We'll take an expression like this, log base A of u squared v cubed, and write it in this way. And then we have a rule for finding the derivative of each term by term. And so that's probably what you'll use most often next year, what we just did. Yeah. Oh, sorry. Luigi and then expand.
Why is it log base 3 there?
Log base 3. Oh, that shouldn't be log base 3. Sorry. Is that what you're raising your hand about saying? Yeah, it should be log base A. It's got to be the same base, or it doesn't work. It's got to be the same base. I can't switch bases on there. Sorry about that. So log base A of u squared plus log base a of v cubed, and then move the powers out in front. That's it. Number 11 here. Let's see if we can break this up into a sum, difference, logs, or factor of the power out in front. So what would be the first step? What's log of the quotient of 2?
Log of x cubed.
It would be log of x cubed, yeah. Yep, and what symbol will go in between the two? You get a minus sign, yep. And then one more step. We can move the 3 out in front, so 3 ln of x minus ln of x minus 3. And there is no rule for the difference of two terms that you're taking the log of, so we just leave that alone. All right, this one's got all kinds of stuff going on here. Different ways you could approach this. I would probably just approach this in the same way we did number 11. So we'd take log of this whole thing, x squared square root of x plus 1 minus log of x minus 2 squared. I'd probably do that first. And then you probably can see that, yes, we do still have a product here, right? X squared times square root of x plus 1 is a product. So to take that product and break it up, I'm going to break it up into a sum, right? So this will be log of x squared plus log of, I'm going to rewrite this as x plus 1 to the 1/2 power. Didn't say anything about how to deal with square roots, but this is the same as log of x plus 1 to the 1/2 power. That square root is the same as 1/2 power minus log of x minus 2 squared. And all that I'm doing is demonstrating that I have 3 logarithmic expressions, and each of them has a power. And so I'm going to apply that third law up here, which we called the power law, and write each of these powers as a product. So move the 2 out in front here, this out in front there, this out in front there. So it's 2 log of x plus 1/2 log x plus 1 minus 2 log x minus 2. And that's the final rewrite of that. And as we typically do in mathematics, we are going to take these logarithmic expressions, and we've taken these and actually made it look more complicated. Usually when we think about simplifying, we think about what we're going to do next, is taking multiple expressions and bringing them into one. But in fact, this is what you'll do more often in calculus. Break it off into those pieces. So if we wanted to solve an equation, we've done this already. If we want to solve an equation with logarithms in it, we usually want to break it down, or take it and make it a single logarithmic expression, and then apply our definition to it, right? Use the loop definition. And so here, in this case, I have log base 2 of 1 over x plus log base 2 of 1 over x squared. And the product rule says this is the same as log base 2 of 1 over x times 1 over x squared, which is a single logarithm. One way to write it would be log base 2 of 1 over x cubed. We could just leave it like that. So just the product of the two things. Number 14 has a subtraction sign in between the two. I also can see here we have a 5 out in front. So there's a couple things happening here. If I rewrite this, it's log base 4, so that's my single logarithm. I'm going to take the x squared minus 1, place it on the top of the fraction I'm forming, and by the power rule, I can take what I've underlined here, that 5, and move it up as a power on the x plus 1 if I'd like. So that would be x plus 1 to the 5th That's one way to, we've actually written it as a single logarithm. Do you see any way in which we could simplify this? We actually can simplify this, believe it or not. It's not obvious. But if you factor x squared minus 1, what does it factor as? Yeah, there's two factors, right? You see where I'm going with this? It's x plus 1 and x minus 1. Well, I happen to have on the bottom x plus 1 to the 5th. So I could actually simplify this a little bit by canceling out one of the x plus 1s on the top with one of the 5x plus 1s on the bottom. And so this would now be x plus 1 to the 4th. And so I have log base 4 of x minus 1 over x plus 1 to the 4th. Although, really, we've accomplished the writing as a single logarithm, so I would probably accept that if my instructions were the same as that on a test. Right, number 15. It says 21, that is a 21, and then log base 3 of the cubed root of x. So here, lots of things going on here. We can move the 21 out. We have log base 3. I would think of this cubed root of x as x to the 1/3, and then move the 21 out as a power on that x to the 1/3. And then let's just rewrite the rest of this. Plus log base 3 of 9x squared minus log base 3 of, let's think of the 9 as 3 squared. Okay. We could leave it as 9. Ultimately, something's gonna get canceled here. But on the top, right here, you see the plus sign in between these two? Also, the power to a power we would multiply. So I have log, let's see if we can write it as a single logarithm now. Log base 3 of x to what power? 7, yep. Times 9x squared all over, so as we move from left to right here, all over 3 squared, or I actually could have kept it 9. It might be better to keep it 9. Or write it 3 squared, because I do have some canceling that happens here. Do you see it? And so we end up with log base 3 of x to the 9th as a single logarithm. All right. I mentioned the other day that change of base formula. This traditionally, this is actually a tradition that doesn't go back as far. It goes back as far as the T83s. You notice. Remember I said that on the T84s and left, we have the log base on the math menu under A. So that one they programmed in the change of base formula for you. But the change of base formula, traditionally we would use to change bases like 3, 1/2, pi, 12, 2, to a base that we could evaluate on the calculator, which was log base E or log base 10. Okay. What the change of base formula says here is that log base B of V is equal to log of V over log of B. The way I remember this is that bases, it's log of the base, has to go on the bottom. The base holds things up, right? So it's always log of the base on the bottom and then log of the argument on the top. Argument is another name for answer to the exponential equation, or it's what you're taking the log of. That's called the argument. So it's log of the argument over log of the base. If you could just remember, the base always goes on the bottom. So we've changed this from base B to base, it could be base C. We could change it to any base we want. But in this case, I've changed it to base 10. It's not written, so we're going to assume base 10. Okay? So it's a way to change something from, say, base 3, like I have right here, to something base 10. Or, even more commonly used is probably to change it to base e, and it's just have ln. So you can rewrite this according to the change of base formula. It's log of the argument, so log of, what's the argument in number 16? 21 over log of the base 3. Or if you wanted to, you could also write this as ln of 21 over ln of 3. And those are the two most commonly used bases. You could do either one. We think we went through this process the other day with the calculators, right? We did log base 10 of a number over log base 10 of another number, and we got the same thing as if we did ln of the same combination. All right, so just make a note that these are the same. You could change it to any base. You could be goofy and change it from log base 3 to log base pi if you wanted to. It wouldn't matter. But it's a way to evaluate it on your calculator. If you have the TI-84, you could do that. You might even want to. Let's just take this, put that down there. So just make a note of that. So here, this would be log of 15 over log of 1/2, and your choice if you want to use log base 10 or ln. And what would this be here? Yeah, log of e over log of pi. Now, if you wanted to be real cute here, if you used ln, if you used ln instead, you could actually simplify this a little bit more, because ln of e is equal to 1, yeah. So lots of options. You're going to notice that as you look at solutions in the back of the book to the homework problems. Even as you go into calculus, that when logarithms are involved, they can be written in many different ways, okay? As a matter of fact, I could even rewrite this on the bottom here as a difference of two logs. Log of 1 minus log of 2 on the bottom. So lots of different ways things can be written. You just got to be aware of that. You're going to see a lot more of this as you move through math here and go into college math. Okay, logarithms and then trigonometric functions. We're going to see a lot of that. There's lots of applications of that. So your assignment, it shouldn't take too long, but here it is, 5.5, page 308.